Hello, welcome to Bedroom Builds at the From Python to Rust series, episode B, traits. Continuing from the previous episode where we talked about error handling. So traits are basically describing functionality or behavior that a type has or shares with other types. And with this, you can then also define trait bounds, where you can, for example, for your function, limit the arguments, what behavior or functionality you expect of the objects that you can pass into your function. You can think of them like interfaces in some programming languages. So this word is used. They're not 100% the same concept, but they're very similar. And the same is true for mixins to a certain extent. In Python, you would use mixins to do a similar thing. And for most of the traits that are kind of nice to have when they're implemented, if you write a library, would be the Python magic methods like dunder str or dunder add for operator overloading or representation purposes, or making something callable, for example. Right, hop over to the code. This example code about the defaults we already had in our episode about structs. What we did is we imported the default trait and implemented the default trait down here for our struct D. And up here we did something special that also comes with traits, is the derive attribute, and you can pass it traits to automatically implement for you. So these are proc macros that will, in this case, do the debug implementation for you. This makes it easy for you to print all the values of all the attributes of your struct D. And in this case here, we add partial equality as well to have an easy to use equality operator. So on the left in Python code, you can see a similar solution using the dunder string implementation for the debug and the dunder EQ for the equality. For operator overloading, I am doing it down here in Rust using the impl keyword to implement a trait. I have fully qualified it here, so I'm using the standard namespace operations add trait. Then this I implement for my struct called the D. I have to define the associated type called output to know what will be output of my implemented operator add. This, in this case, it will be D, because all we are doing is just adding the attributes to each other. So we recreate a D after our operation. The associated type will help you to implement other things. So if you, for example, add a string to your type, your output will likely also be a string. And then you can implement a second operator overloading for strings that will have a different output. And that's why you have the associated types, because otherwise implementing the same trait twice will not yield this example just like that without the associated types. Now, one cool thing that I explained at the top is the derive attribute. I already told you for simple structs that already have a debug for all the properties implemented, you just can use debug and it does all the code for you and partial EQ. Now we have meticulously implemented default here, but we actually can get rid of this and do it in a simpler way, because all we have to do is go up here and use the derive to do it for us. There's lots of traits that the derive can implement for you. So read the documentation. This is very helpful, and this way you avoid to write code that was not necessary to be written. Let's check if this stuff actually works. So we call the Rust compiler on our defaults rs. It works fine. And we call it as well. And we get our output. You can see in the second line, this is from our addition. So we added the two D's up here. That's why this X is 2 and this Y is 4. The default thing works fine. So our derive attribute did the job for us, which is really nice of the Rust developers to give us this functionality. If we now run the Python thing, we can also see that everything worked as expected. Here we get our output of the addition, and the assertion of the equality works out in both cases as well. This means the two codes are equivalent. If we check again on the main code what is happening, we create our two D1 and D2 thingies. Then we do an assert equality in both cases, and it works out. And we print and check if we have the debug output implemented. We have, and the plus operator is overloaded. Great stuff. Generally speaking, there are more interesting and intelligent traits that exist already. So for example, the debug one is for debug output, but to have proper string formatting, you should actually use the display trait. Then, for example, converting from another type into your type, you can implement, for example, from or try from. This will then allow you to parse from strings into your data type, for example. This way, every other Rust programmer will know what's happening, and nobody gets to invent their own interfaces for common things that are out there. So please read the documentation. This will help you a lot to avoid writing code, like for example a derived default will help you a lot to not write boilerplate on your own. And the same is true for many, many other things, not just those three examples mentioned up here. I will have to quit on the right side, hop over to our code that we already used for iterators, because here we can show another interesting trait thingy. Let's open iterators in Python as well. Implementing the iterator from the episode about iterators looks like this. You can see it on the right. You implement the iterator trait for a counter. You again have an associated type to know what your iterator will return. You implement the next function and you're done. Basically the same here on the left in Python. You implement the dunder next and the dunder iter, and you have an iterator. And what I've added here, which is an interesting trait that you can use to handle, for example, open connections and stuff like that behind the scenes for your user of your library. So if you implement, for example, a connector to a database, then you will construct your object. This thing will connect to the database. And when it goes out of scope or a user actively drops it in his code, you can then clean up after you, closing the connection or freeing some other resources without having to call a certain API function that the user of the library might forget about. You can implement the drop trait to do that. And all this requires is for you to implement the drop function. So let's suppose you have this database connection thing here. Instead of the print here, you would close the connection when it goes out of scope. The same thing in Python as this drop trait is implementing dunder_del, as you can see here. So when you call the delete or it goes out of scope and the garbage collector is ready to clean up your object, this will be called and you can do stuff in here. To actually clean up resources after yourself, it is better in Python to use context and implement context and not using this, because you have no control over when the garbage collector will fire. So use context for my example with database connection, for example. The actual code of the main has not changed. So on the right, it is just testing code. On the left, we have the delete. But I can show that this destroyed at or dropping at code actually executes. So in Rust, we can use cargo test, and then we use no capture to show standard output coming out of a test that succeeds. And let's run this, and it will actually show us the dropping at 5 3 times. Why 3 times? We can quickly figure this out in the source code. If we go down to our tests, we can see that in our first test we create one counter. It goes out of scope here, so we get our first one, the destroyed one, and here we create 1, 2 counters, so that's why we have 3 outputs, 1, 2, 3, and all of this happens when they go out of scope, so basically right before this curly brace. On the left, we can also show this for Python. So Python iterators. Here we have it 5 times. Reason is also easily explained. So the 5 times are happening because we have 1, 2, 3, 4, and 5 counter instances. Therefore, we get this destructor output 5 times in a row. On the right, I have an example that only makes sense for Rust programmers. So I will not have a Python equivalent. Let's hop out of here again, go back. Let's edit our return trait example. Here we can see that we can not only implement a trait for a struct, we can also use it to set trait bounds or to define our expected return functionality or for return values behavior. So in this case, we have our function definition, and the return is of type function that takes an argument i32, and this function will return an i32. What we do then inside the code here is we create the closure that takes an argument x and adds y coming in from the argument up here, and returns this closure variable. Now this closure is of type function. It takes i32 as an argument, and it does some math, and all it does is return an i32 because it does math between the i32s. And this works. Down here you can see how this works. So you can make an adder function that adds 1. Luckily this was called +1, so people using this variable will understand what will happen. So if you call +1 with 2, this will equal to 3. This works fine. So the impl keyword you can use for return types as well. And in our next code, I will also show you how you can use this declaration for function arguments to create a trait bound to make clear to the user of your library function what you expect of the objects that come into your methods and functions. Let's jump over to this one. Super traits RS. Let's go to line 1. I have implemented something similar in Python. Let's quickly go over the code. So the first trait we have is a trait called person. This person has a name, so we expect the name method to be implemented. In this case, we have a default implementation that just returns the string unnamed. So here you can see the trait student, and it derives from person. So this is almost object-oriented hierarchy programming if you want. So now if you implement the trait student, it will be expected from you to also implement the trait person. Here we have the function university that returns a string, and you can see right here is already the semicolon, so this is not implemented. If you forget to implement the university method, your code will not work. Then we have a trait called programmer. This is just a trait on its own. The programmer has a favorite language, which is also not implemented. Then we have the computational science student. This person happens to be a programmer and a student happens to be a person. So this comp sci student actually supports all the traits listed here. And to show you how this works, I implemented all of those. So I created a random street person, a college student, a Rust programmer. So all this person does is Rust programming. Artificial programmer, so that's not a real person, but this artificial software programs nonetheless. And we have the amazing super computational science student. Now here you can see that I can implement person for street person, and I don't have to do anything more. Like this is a valid code line, and the reason is up here we have this default implementation. It will not be working well because when you create a street person with a certain name, it will still return unnamed for you because the trait up here, person, is just a trait. It has no concept as to where you are going to apply this trait to. So we cannot access self and some attributes of self. Because at the point in time of definition of a trait, the compiler has no clue what this will be applied to, so you cannot access properties. On the left here in Python, you can see that we have this class person. You give the person a name, and we have this name method implemented that will return the name to you, and this will always work fine because whatever name you will use for the constructor will be known by the object, and this will work fine. If you wanted to have the correct name returned, you cannot use this single line of code to tell the street person is implementing person. You will have to implement the name method, like here, returning the correct thing, which is what I have done, but not for street person, as you can see. But I have done it for the comp sci student. So you can see that in the center here of the code. So for the super comp sci student struct, I implemented person, the name method, and then self.0.clone. I have to clone the object because it is a string that we are storing in our struct, and if I want to return it, I cannot give up ownership. I have to make a copy. Therefore, I use clone. Yeah, here you can see our artificial programmer is not a person. We only implement programmer for it, and it can program any language. Of course, it's artificial intelligence. Then I created a college student that goes to community college. Our comp sci student knows 2 programming languages, goes to a certain university, and his Git username is just his normal name and lowercase. This more or less covers the code. Let's go further down to our function definitions. We created a function called computational science student greeting that takes a student, and in order to accept everything that has the trait comp sci student implemented, we use a reference, the din keyword, for being dynamic. So this is now a generic function. This adapts to whatever struct you implemented comp sci student for. And this is now the trait bounds that you can use to allow only a certain subset of structs in as an argument, because if you have not implemented comp sci student, the compiler will complain because it cannot use all of these methods afterwards. Right. So what this does is it formats a string, taking all those methods. And below, we have a function that does the very same as the one up here. It is just defined in a different way. We use here the generic type t that has to have comSciStudent implemented. And then your argument list becomes a bit easier to read because you just use the %t to denote what's going on. If you have multiple arguments, then this might be an easier way to read. And right below, yet another method of how you can use your trait bounds. So you can code up your comSci versus programmer function using the abstract types t and u. Then you have your two arguments called student, that is a reference to the type t, and the programmer, which is a reference to the type u. And below, you use the keyword where with the abstract t type being of comSciStudent, and the u has to be a programmer. So you have to implement the trait programmer, and this has to have implemented a trait person. So just programmer will not be enough because we use the name method, which is coming with the trait person. And there's way more cool stuff you can do with this where keyword. And defining your requirements for a trait, you can also, for example, use the exclamation mark to filter everything that has a trait implemented, even though it's not supposed to have it, for example. Okay, now we have covered arguments using trait bounds coming in. And now we can also use this as a return value. So I already showed you the example where we returned a trait of type function. But here we now have a function that gives us, let's hop over to this code, line 95, center this up. So here we have a function called makePerson that takes an integer number and it returns something that implements person. But person is only a trait, and all of these structs that we are constructing down here, so street person, college student, Rust programmer, and supercomSciStudent, can be of different size. The compiler, though, has to know the size of your data types at compile time. In order to do this, you have to use the box type that uses the generic input information din person in our case. The size of box is known to the compiler because all this holds is information of the pointer to the object that was created on the heap. So the size of a box is known. This is basically just pointer information. And this way you can return something that implements person, and that way the compiler is happy. Below here we use the match statement to figure out which number that the randomizer spat out will generate which type of person. And the dunder down here, for people that haven't seen pattern matching video yet, this is just for any other case except those numbers. You will get a supercomSciStudent, and all of these will have a different name. Remembering from back up in the code, this has no consequence because mostly I did not implement the name method. I hop down to the main code now to see what is happening. At first, I did not implement the randomizer. I will simply call makePerson and the number 8, which will give us a Rust programmer back as a person. We print out the person's name. After that, we create a comSciStudent called Bert. Then we call the greeting function, and below the other one that simply use a different function signature to show the two ways of how you can use trait bounds. And below we create a Rust programmer, and then we use our comSci versus programmer function. And here, just to show you how the compiler will react if we do something it doesn't like. Now on the left, I tried to implement similarly what we've done in Rust in Python. So I created a class person, the class student that derives from person, which you can see here. Then I've used the ABC module and the ABC meta class and the abstract method decorator to create a class programmer that is a meta class. Then I can define something, an abstract method, and this basically forces the implementer that derives from the type programmer that he has to implement the favorite language function. And up here, I do a trick that is a bit more stupid, but works as well. You just create your type student that derives from person. You run the constructor and the constructor with super of the parent. Then you define your abstract method without telling anybody that it is an abstract method called university, and you raise the not implemented error. So if somebody then uses it and forgot to implement university, you will get this error raised. The better way potentially is to use the ABC meta way of doing things. Down here, me being lazy, I did the trick again. Now let's scroll further down in the code. We have also the Rust programmer. Now this is a person and the programmer. And this favorite language is Rust. And then we have also our super comp.sci student, which is a student and a programmer. Student, remember, happens also to be a person. Therefore, we have the name implemented. Here we implement favorite languages, university, and his Git username. So we get the same functionality, more or less. Hopping even further down in the code, that was too much. We now get the equivalent of, which you can still see on the right here, the make person function. Since I'm using now again the normal Python version, I don't have pattern matching. Yep, street person is happening and all the other stuff exactly like here. And then we have our comp.sci student greeting. Down here, I create a person, I create a college student, and we try to use that for the greeting. Now let's run this Python code first. This means hopping over, then swapping to Python, Python superpy. It does not work because what we are doing here is we're passing a make person 8, which returns us a Rust programmer, to the comp.sci student greeting, and this will error out because the Rust program object has no attribute called university. Let's quickly fix that up by simply passing ten here, which will give us a super comp.sci student, and for this it will work. Let's see if that is true. And it is. So here we see the advantage of Python. It is very easy to just define the name function once and it will work fine. So Bob is in community college and Bert will attend his alma mater and has his favorite languages. Now let's run the stuff in Rust. So we Rust compile our supertraits.rs, works fine, and we run supertraits. So here we see the first issue. Unnamed is the output of the person that we've created. So the Rust programmer Robert doesn't keep his name in our case because we did not implement the name function. For this one, we rely on the default implementation. Then below here, we create our birth student. Since here we have implemented the name method, the output works fine. So birth doing everything twice, it's exactly the same output because we call the same function, simply with a different signature. And then here again, the problem with the unnamed, the programmer likes Rust. And then below we get a working comp sci versus programmer output. These are these two lines. Now, if we change the source code on the right to let the programmer be the artificial programmer, remember, which is not a person, but the function comp sci versus programmer expects programmer and the person to be an implemented trait for the second argument. We will see that the compiler does not let us compile that. And he even tells us exactly why the trait person is not implemented for artificial programmer, which is true. This way you have way more control of what is happening. What we did in Python was simply pass in an object and ask it to use the hopefully implemented methods. If it doesn't have it, it will fail on us during runtime, and we have no control before the runtime to understand that this is a potential problem or not. Now let's remove this code and see what happens if we do what we did in Python actually, because what we did there was we tried to pass the object that came out of the make person. You can see it up here. Make person 8 gives us a Rust programmer. So in theory, if I replace at the end of our code the variable with p, it should work, one would think, because here we get a Rust programmer. So I'm passing here Rust programmer. Rust programmer, we've seen using the prog variable, works fine because it has implemented the two traits needed. Now let's see what the compiler says to this effort. Let's clear the screen first. So here it tells us that the trait programmer is not implemented for the box person, and that is true. So even if we were able to take the person out of the box and hand it over, it would still only be a person to the compiler, and it wouldn't know what to do with it. And here it again then complains, as it did before for our artificial programmer, person is not implemented for that either, because we have this box type. Now that makes it a bit harder in Rust to do stuff, but then also way more precise and correct. This means, yes, you have to write a bit more code, but it will be way more efficient, and you know at compile time already that stuff will work or will not work. If I wrote the code to how it was before, we can see it compiles again, and this also tells us it will work in every case. For the problem that we had in Rust, for being too lazy to re-implementing the name up here and implementing it for every struct using this function, there is an RFC that will allow traits to access attributes of your structs, but this has been postponed to much later, so this is not in the near future coming to Rust. You will have to redundantly implement that, or, which I will treat in a future episode, you can create your own derive compatible macro using proc macros. So then all you have to do is use the derive attribute for your supercomp_sci student for your person type, and this will generate this code for you, and you do not have to redundantly write the same code all over the place. Right now, this is needed. We have to live with it. That's the downside of a fairly new programming language. But given the performance improvements and the resource economics, it's still worth it. Thanks for watching. Coming up next on the From Python to Rust series will be operator overloading, where I will discuss that even more in detail, because today we only scratched the surface of how this works.